Morning. Good morning, everyone. Раз. Good morning, everyone. I am Fedor Fomin from the University of Bergen in Norway, and I will give you a tutorial or introduction to parameterized algorithms, the basics of parameterized algorithms. Just to start with, how many of you heard about parameterized algorithms? That's good. And how many of you know the definition of FPT? Okay. So I will try to go very fast then from these definitions, and so what will be all this lecture about? So you already heard about polynomial algorithms, and I think the last 2 days you spent on different variants of matching problems and different type of algorithms for that. So there are problems which are solved in polynomial time, and there are problems which are NP-complete, and there are some other problems. And basically, what all these things are, or all these parameterized algorithms are about, just let me start just from an example. So favorite problem, vertex cover. And in this problem, I have a graph G. I have integer k, and the question is the vertex cover of a graph G at most k, right? And the vertex cover is the set of vertices such that every h in the graph is adjacent to at least one of the vertices from this set. So these are, so for example, in this graph, vertex cover here is this vertex, and this vertex, they form a vertex cover because every h is covered by a set. Okay, this is a classical NP problem. On the other hand, if I ask you, can you find what will be the algorithm for computing vertex cover? Not polynomial time, but maybe even exponential, right? So the simplest algorithm will be the following idea. I just try all possible sets of size at most k, right? And choose k. And then in polynomial time, I check if what I guess is a vertex cover or not. So this is times m. I put a big O, of course. And then I have something like n power k plus 1. Actually, actually, so when k is a constant, this is a polynomial time algorithm. And there's no contradiction here. It's not that we solve NP-complete problem immediately. It's just because all hardness reduction for vertex cover, they work only when the number k is close to n. Then this running time, n power k plus 1, will be exponential. But the question of parameterized complexity is not about that. So the question is, okay, so we have this naive algorithm of running time, n power k plus 1. Can we do something better? Of course, you can say, no, we cannot do anything better because otherwise it will show that P is equivalent in P, and then that will be a complete disaster or a complete amazement. So whatever point you take on that. So, but most likely it's impossible. But still, P and NP, it only says polynomial and exponential. But maybe vertex cover could be solved in running time. For example, maybe the running time could be, I don't know, like k to the k power n square, or maybe 2 to the k power n square, or maybe something else, right? And actually, it happens with vertex cover. So vertex cover, it's possible to solve vertex cover in running time f of k. So this is just some function which depends only on k. K is a parameter here. That's why it's called parameterized algorithm. And then it's polynomial of the input size, the number of vertices in the graph. So this type of algorithms, they are called fixed parameter tractable. Or just FPT. And all game is when we look at a parameterized problem. So we have a problem, we have input size, we have a parameter. And then the question is if there exists a parameterized algorithm, so the algorithm of this running time. Or there's also tools which show that it's impossible to obtain such type of algorithm. There's a complexity theory. I will not speak about complexity theory at all in this lecture. And then the other thing is the other game. As far as we establish that the problem is fixed parameter tractable, then the game starts, could we optimize this function f of k? Because could it be maybe function k to the power k to the power k, or maybe it's a function of k to the k, or maybe it's k factorial, or maybe it's 2 to the k, or maybe it's 1.1 to the k, right? That's a different game. And actually, one of the motivations is, of course, we are dealing with the NP complete problems. There's intractability here, and it's you cannot hit the wall completely. But still, you can maybe make a small steps here. And at the end, so if we have an algorithm of running time, for example, okay, if you have an algorithm of running time n to the k plus 1, and if we have an algorithm of running time 2 to the k times n, of course, the question is which algorithm is better, right? Both algorithms, both running times are exponential, right? So if you look at when you take the first course in algorithms, the first mantra we learn is polynomial is good, exponential is bad, right? But we have an NP-complete problem, exponential is bad, not much we can do with that. But still, exponential, and if you start playing with numbers, for example, if you want to solve a vertex cover on a graph with 1 million vertices. So if you want to find a vertex cover of size 5 in this graph, you are dead already, right? But if you are looking for this running time, so with this running time, you can, I would say, if you are skillful in programming, you can solve it for the k equal to maybe even 30. Right? So there's a huge difference. And these functions, they're both exponential, but the exponential growth is different. Okay, that's the whole motivation behind what is a FPT and parameterized complexity. And my plan is to give an overview of 3 basic techniques, or maybe even 4 basic techniques used in parameterized complexity. One. It's okay. It looks like the sound disappears from time to time, so it's like okay. So the first technique is it's the first technique which you ever use if you want to design a parameterized algorithm. It's called the branching search tree, or a branching, or a pruning search tree. There are a lot of different names for this technique because it's so natural that people come out to these methods in different areas of computer science. And I will give examples with vertex cover, 3-hitting set, feedback vertex set, and tournament. And then the second, also very old technique, which comes to Bellman from 1960s, is called dynamic programming. My example will be graph coloring. And then we'll come to more interesting and more funny techniques. Both methods are randomized. One is called color coding, and this is a very beautiful algorithm which solves the longest path problem. And then I will speak a little bit about another randomized method called random separation. That's overview of my first lecture, and we will see how fast we can go with that. Any questions so far? Okay, and please just if something is unclear or I am saying something wrong, right? This could happen. Just stop me, raise your hand, or interrupt me. Okay, at least that will be a good sign that you follow what I'm saying, right? Okay, bounded search trees. Again, favorite example: vertex cover. Vertex cover. Once again, what is the problem? I have a graph G, I have an integer k, the parameter here is k, and the question is if I can find a set of vertices of size at most k, such that every h in my graph contains at least one of endpoints from this set. So in this example, yes, I have a graph, and here is the vertex cover. And you can check that every h is covered by at least one of the vertices. Okay, so we start from the algorithm for vertex cover. And the first observation is extremely simple. I have an h, let's call me u and v. So this h and every vertex cover should contain at least one endpoint of this h, right? It should be covered. Okay. So I consider this algorithm. So if I have in other words, if my instance g k is a yes instance, it means it contains a vertex cover of size at most k. Then if I take a look at two other instances, in first instance, I remove vertex u and I put it in vertex cover. And in the second instance, I remove vertex v and I put it in vertex cover. And I also decrease the parameter by 1. Then if my initial instance was a yes instance, then at least one of the new instances also will be a yes instance. Right? Agree. Okay. And actually then this is the algorithm, right? Nothing else. What I'm doing? Okay, I'm just repeat this argument. So if I reach the situation when my k becomes negative, I say no, there's no vertex cover of size at most k, right? Or if g has no edges, I cannot branch anymore, I say yes. And then if my graph contains an edge, I continue branching. I just go recursively in two instances. So this is the algorithm, right? Let's see. Yes, and why it's called bounded search tree? Because it's very natural to represent this algorithm as a branching tree. So in this branching tree, I start from an edge in a graph, right? And here I go in two children corresponding to the endpoints of that edge. And so then I go, so here in this example, in this branch, I stopped branching, and in this branch, I continue with another edge, right? Okay, so what is the height of this tree? Look, on every level, I reduced my parameter k by 1. So I cannot go more than k floors below in this tree. So this means that the height of this tree is at most k. And then what is the running time of my algorithm? So the running time of my algorithm, at every step of branching, I'm using polynomial time, right? It's like I found an h in the graph easily doing any of your favorite search, and then you just do this branching. So for every node of the tree, I spend actually linear time. So then it means that the exponential part of my algorithm is proportional to the size of the tree. Okay, I have a tree of size I have a tree of height k, and it's a binary tree. So the number of vertices is then 3 is at most 2 to the k, and the running time of the algorithm is 2 to the k times polynomial of n. Right? So first of all, this means that the problem is fixed parameter tractable immediately. And then the second question which comes, the first question which comes if you are doing algorithms, the first question you should ask yourself when you have an algorithm, can I improve the algorithm? Of course, you ask standard questions. Is your algorithm correct? How fast it runs? All this. But then you start thinking, okay, if you're a researcher, you start, is this algorithm the best I can do? Or I can do something smarter? And for that situation, of course, sometimes it's even easy to see that your algorithm is optimal in the sense that this is the algorithm, and you can construct examples of graphs where your algorithm will take exactly the time what you predict. And here is exactly the case. For example, so what is the worst case example? I take a graph which consists of k matchings. And look how our algorithm will work on this graph. I will take, for this matching, I will branch on 2 subcases. Oh, sorry, on this H, I will branch on 2 subcases. On this H, on 2 subcases. So I will have a complete binary tree as the result. So on this graph, my algorithm will have to take 2 to the k steps. Right? So this is unavoidable. So my algorithm is optimal. No, what I'm saying. Yes, yes. So the analysis of the running time of this algorithm is optimal. It's not like I don't want to miss anything. But on the other hand, you can start saying, wait, this is the worst case example. But in this worst case example, all vertices of a graph are of degree 1. But in this case, you can solve vertex cover very efficiently, right? So basically, so what's you just take any for any H, you take 1 vertex from the H. So what's the point, right? So you can say, aha, okay. So if my graph has all vertices of degree 1, actually I can solve this problem in polynomial time. And let's see what branching does for other vertices. Okay, so this is the vertex. Okay, then let's just make another observation. So if I have a vertex V in a graph of degree at least 1, then for every vertex cover of this graph, either this vertex is in a vertex cover or all its neighbors, right? So how come? So this is example, this is the vertex V, and this is its neighbors, right? So I'm saying that either this vertex should, I have to cover all these edges. So then it means that either this vertex should go to vertex cover, or if it doesn't go to vertex cover, then all these neighbors should go. That's what I'm saying here. Okay. So in other words, it means that if I have a G, if Gk is a yes instance of vertex cover, then it's if and only if yes instance. If either the graph obtained by removing V from G and reducing the parameter by 1, or the graph obtained from G by removing the neighborhood of V and then reducing the parameter K, is also a yes instance. Okay, so then, yeah. Sorry. Here? Yes. Yes. If you say that, yes, it should be yeah, at least yes, at least 1. Yes. Because if it's 0, then yes, I don't have to take the vertex and the vertex cover. If it's 2, that's okay. I just don't understand the question. You ask if the vertex of degree is at least 1. Yeah, it's yeah. Yeah. Okay, so I just repeat the same arguments with a small modification, which I did for the most primitive branching algorithm. That's exactly the same. So if my parameter is negative, no. If I have a vertex, if I have no vertex of degree at least 2, I solve the problem in polynomial time. Right? All vertices are of degree 1 or 0. That's okay. And then if I have a vertex of degree at least 2, I am doing this branching. So and then this branching I branch into subproblems. One subproblem I reduce the parameter by 1, and the other problem I reduce the parameter by the size of the neighborhood. Also, it's an open neighborhood. It's a neighbors. They do not include, because you say either I take this vertex or I take the neighbors. And if you think about closed neighborhood, in some case you can have both of them, but this case will occur either in one subproblem or in other. Sorry, say louder. Yes. Yes. Yeah, okay. That's a very good question. So the question I just repeat for the online audience. The question is: if I remove all neighbors of V from the graph, V becomes isolated vertex, And then I can also remove it from the graph. Yes, this is for sure, this is true, but I don't want to handle this. Why? Because this vertex, anyhow, it becomes of degree 0. So this will happen to me in this case automatically, right? Because this vertex will contribute to this case at some moment. Yeah, but if you want, you can also remove it. That's perfect, also perfectly fine. No mistake. Okay, what is the running time of this algorithm? So basically, running time. So here, if I estimate the exponential part of the algorithm as t of k, then this exponential part of the algorithm, it's my worst type of expectation. In one branch, I reduce the parameter by 1, and in the other side, I decrease, and in the other part, I decrease the parameter by at least 2. Okay, and it's 1 otherwise. And then the usual trick is you search, you estimate this running time as a single exponential function. And basically, yes, there is some mathematical proof. I will not speak about this. That solution to this type of recursion is always in this form, in this exponential form, right? So then, so I just will rewrite this as this inequality, right? And I divide by alpha k minus 2. So I receive the following. So I received the following inequality, and this means that my alpha should satisfy this alpha square should be at least alpha plus 1. Okay, this is already the even not a high school arithmetics, right? No, not arithmetics, it's algebra, right? Okay, so we solve quadratic equation, and yes, we're looking only for positive root, right? Because one will be also negative. So this is so this is the positive root, and this means that actually the function t of k is bounded by 1.6 something power to the k. Okay. So far, so good. But then we can start again, ask the same question. Okay, so it looks like our worst case estimation of this algorithm happened when of a graph is 2. But again, what means that a degree of the graph is at most 2? It means that every connected component in the graph is either a single vertex or a path or a cycle. But if my graph is a cycle, I guess we can solve vertex cover in polynomial time, right? Shouldn't be a problem. If it's a path, we also can do, right? So it looks like, again, we do something silly, right? Because the worst part in our algorithm, branching on vertices of degree 2, it's polynomial time solvable case. So I'm doing the same thing, right? So I can just change my algorithm and say, well, if all vertices are of degree at most 2, solve the problem in polynomial time, otherwise branch. This will give me this running time, or this recursion for the function t, which brings me to this running time, to this estimation of the function lambda. And here I should have lambda, of course, at least this, which doesn't matter. And then this immediately gives me the running time 1.4656. We can I can say it doesn't matter, right? Because anyhow, yes, that equality is also okay, because anyhow I'm doing the worst estimation, and this is yeah. Okay, so this is the algorithm 1.4, and now you got the idea, right? You can go further, right? Now you can say, okay, let's look what happened at vertices of degree 3. This is a nice case and solve, but here is a problem, right? Because when I have a cubic graph, I know that vertex cover is NP complete on cubic graphs. So unfortunately, you cannot continue this type of nice arguments going further and further. So the block stops here. It's a degree. Okay, and then the natural two questions. First of all, when so I have this estimation for the function t of k. Is it the right estimation of the function t of k? And this is the easy question, because it's easy to show that yes, if I have this recursive function, then this recursive function really behaves like that. So it's yes, but the other thing is, which is much more interesting, and it's much less clear. So I have this algorithm, branching algorithm on a graph. But is the running time of this algorithm, or is it tight or not? And basically, why I really don't know, and it's a difficult question, because what's happening? So I tell you the simple algorithm, right? I have a vertex of degree at least 3, I branch. But when you do branching, you also you remove vertices of the graph. You also changed a lot of things in the graph. You also decrease for example, you decrease degrees of some other vertices. You create some isolated vertices. You do a lot of nice and strange things. But this type of analysis, it doesn't capture this type of behavior. Right? So, and this is a really interesting question. If even branching algorithm is, if its running time is 1.4, or it's much better than 1.4 power k. And actually, also, you can try to add more branching rules, more ideas to the algorithm. And people are doing this for quite a long time. And actually, there is the current record is this algorithm. Okay, so the current best running time is this 1.7 to the k. And actually, this was an unbeatable. It's not mine. So it's, okay. Okay, thanks. Yes. Yes. So this algorithm was unbeatable like for 10 or 15 years. And actually, quite recently, I saw on arXiv that people were improving this algorithm up to the somewhere in this digit. So still there's some work happening here, but this type of algorithms become quite complicated branchings and also quite complicated analysis of the running time. Okay, so but more in general, so when we have a branching algorithm, right? So in branching algorithm, we always try to reduce the parameter, and the general linear recurrence of this type of algorithms is of this form. And the solution what we search for are like in the form of this polynomial, which brings us to this thing which is called characteristic polynomial. And it's also possible to show that this type of characteristic polynomials, they have a unique root, branching number corresponding to the branching vector. So in this branching vector, basically what we are saying that this branching vector, it just corresponds to the constants for which we decrease the parameter in every sub-problem. And of course, people doing this for ages, and if you start doing branching, so one thing could be that you just write your own program which has to compute the roots of the polynomial, which is doable, right? But also, before doing this, be aware that at least for small values of these polynomials, all these things are already computed. Yes, and this is just the example how good the branching could be. So, for example, if for vertex cover you manage to branch on the you manage to branch the situation when in one case you reduce in one subproblem you reduce the parameter by 1 and in the other by 6, then you will get this running time to the k, right? Yeah. Any questions? No, just yes. But okay, let me just the usual thing. I explain you the idea, and now I take just another problem which looks similar to what I already explained. And then I will just try to apply the same ideas, and we'll see if they work or not. So the similar problem is called D heating set. So here I have a universe U. I have a family A of sets of size D over the universe, and I have an integer K. And then the question is there exists a subset X of U of size K that has an empty intersection with every member of A. And here is the example of this, of the yes instance. Sorry, here's the example of the heating set. So in this heating set, I heat all, so I have 4 sets. So each set consists of 3 elements, the square, and the heating set here is 2, right? This element and this element. Yes, and you probably already noticed that D heating set is a generalization of the vertex cover, because vertex cover is just 2 heating set if every H consists of 2 elements, and I'm asking to hit all the sets with the elements of size at most K. Okay, and you remember how we branch on vertex cover. We were taking an H, and then we just branching onto some instances, so here I can do the same type of arguments, right? So if I have a yes, okay, yes, let me just restate it. Okay, so if I have an H, I just branch on 2 instances, right? And the other way of seeing this, right? What I can do with vertex cover, instead of removing a vertex, I can say, in my graph, I remove an H, right? Because I still, in this H, I don't have to cover anymore. And then I reduce my parameter by 1, right? So this is exactly the same. I take the all, and then what I'm doing here, in this graph, I remove all edges which are incident to vertex U. And in this graph, I remove all edges which are incident to vertex V, and reduce the parameter here and here. So this is for 3 heating sets, I will have the following algorithm. If my set of sets is empty, I say yes. If my parameter is negative, I say no. And then I pick up any set of the remaining sets. And then I say, okay, at least one of these vertices should be in the heating set. So I branch on 3 subproblems. I remove all sets containing vertex U. Here I remove all sets containing vertex V. And here I remove all sets containing vertex element W. And in each of the instances, I reduce the parameter by 1. That's the same type of algorithm. And then the running time of this algorithm is 3 to the k, right? Of course, you can look at the branching vectors, you can try to compute the polynomials, or you can also argue with the branching trees, because I have a tree of height at most k, but this time the degree of this tree is 3, right? So it has at most 3 to the k vertices. Yes? This? Yes. S is the set of all sets which contain element U. Right? So it's like so in this example, so S of B, this set and this set. And again, it's like with edges. I can remove these sets just because I don't have to hit them at all, right? Yes. That's a very good question. Exactly. Yes. Yes, this is a very good question. So the question is, let me just repeat the question. It says, okay, I'm doing for 3 heating sets. And for 3 heating set, I have running time 3 times k n of 1. And then the question is, but for d heating set, the running time will be d power k times n of 1. And because d could be of order n, or right, this is not FPT algorithm, right? So this algorithm is FPT only when d is a constant. And actually, there are very strong arguments saying there's a complexity theory saying that it says that there's very unlikely that there exists FPT algorithm for general heating set problem. So you really have to bound the sizes of the sets by constant. But that's a good question. Yeah, that's and now I understand why I disappear, because I think the Wi-Fi is there. So when I come here, okay, I will not play this game. Yeah. Okay. So another example. It's I will go very fast for this example. Feedback vertex set in tournaments. Here I have a tournament. So tournament is just I take a click, complete graph, and I just orient the edges. It's a directed graph. So this is a tournament. So I have a tournament T. I have an integer k, and then the question is if I can have a subset of vertices x in this tournament of size at most k, such that if I remove this set, the tournament, the remaining graph will become acyclic. Or yes, it's also will be tournament, of course, right? So it will have acyclic, and acyclic means that it doesn't have a directed cycle at all. Okay, so do you know how to solve this problem in FPT time? Please shoot. Okay, I will give you one. Yes. Very good. Yes. That you just need you just need one observation, and then as far as you have this observation, you just take everything what was already explained and apply to this observation. And the observation here is the following: if my tournament doesn't have cycles, it also doesn't have a directed triangle. Why? Right? Suppose I have a cycle in my tournament, but this is a tournament. So this there also should be either this edge or that edge. But if I have this edge, then I have a triangle here, and if I have this edge, I have a triangle here. So then what I have to do, right? The question is, I have a tournament, and I have to kill all the triangles. I have to hit all the triangles, and this is a 3 heating set problem. Yes? So this we already know how to do in time 3 to the k. Okay, so dynamic programming technique. My example is k coloring problem. So in k coloring problem, I have a graph, and I want to color vertices of the graph in k colors. And the only condition I insist this coloring should satisfy that if I take any 2 adjacent vertices in this graph, they should be colored in different colors. Right? So this is an example of a 3 coloring of the graph. You see, I'm using 3 colors, and one color, 2 color, and 3 color. Here. Okay. Since you already spent 2 days on matchings, right? I guess you know that 2 coloring is a polynomial solvable in polynomial time, right? Any algorithm for that? Yes. Sorry for asking embarrassing questions. I will not do it again. Yeah, okay. Can you solve 3 coloring in time 2 to the n? Now, to me, n, the number of vertices, is the parameter. So before I was saying that the parameter is the size of the vertex cover or a heating set, but the parameter could be anything, right? So it's up to us. Let's say parameter is the number of vertices in the graph. Yes, it doesn't make sense to make the parameter, for example, the number of colors, because 3 coloring is already NP complete, so it's wouldn't bring to anything good. But number of vertices is still interesting. Can you do 3 coloring in 2 to the n? Yes. Yes. You already had this course, no? Okay. Yes. Very good. So the solution, I just will repeat it. So what's happening? So the solution is we just try to guess all sets of size I. We try to guess one color. This is n choose I, right? And then the remaining part we solve in polynomial time, because the remaining part should be bipartite graph. So what we do? We try a set. We check if the set is independent. That's good. We check if the remaining part is bipartite. If it's good, right, we are done. If we never find such a combination, we say the graph is not 3 colorable, right? And the total time of this is 2 to the n. Exactly. Sorry? I just n choose I. This is called the binomial coefficient. No, so here I just guess one color. I just guess the first color, and if I guess correctly, the remaining part should be bipartite. And I just look if it's bipartite, right? Yes, but yes. So I check a set. I go through all independent sets, right? But yeah, but yeah. And you probably can, if you know a bit more about independent sets, you can say that you can maybe go not through all sets, but only through all maximal independent set, and this number will be not 2 to the n, but a little bit smaller. But I will not probably I will not go to that. Okay, 4 coloring in 3 to the n, right? Now you got the thing, right? So okay, so 4 coloring in 3 to the n is now it's easy, right? Again, I guess everything. Sorry, I guess independent sets, and then I use the 3 coloring algorithm. Okay, so k coloring with the same type of arguments should be possible to do in k minus 1 to the n, right? Okay, but can we do k coloring for in time 3 to the n for any number k? That's the question, right? Somehow, which seems to be more interesting. Okay, so what I will do? I will do dynamic programming. Okay, so the main observation here, okay, so whenever you do dynamic programming, right, it always looks scary when you look for the first time. The second time you look, you don't understand what's happening, right? But after some time, you see that the only thing for dynamic programming you should understand is to understand how the formula looks like, right? So how the solution for my subset depends from the solution from the subsets of the set. Okay, so what's happening here? So if I take a vertex set X, and I look at the graph induced by this vertex set, and I look at the chromatic number or the minimum number of colors I have to color this set X in a graph, then what is this, right? It's 1 plus minimum of opt X minus I, where I is a maximal independent set. This is exactly the same idea we tried before, right? So I just guess the first color, and I always can assume that this first color actually is even not only independent set, but also even maximal independent set. Maximal means inclusion-wise, so I cannot add anything to that, right? And then, so this one color, and then this is the optimal coloring of what remains. It's exactly the same formula which I was using for 2 to the n algorithm for 3 coloring, for example, right? This is the formula. Okay, but then what is the running time, right? So here I go through all subsets and choose I, and then here, sorry, what I'm doing here. Yep. Yeah. Doing here. what I have to keep in my dynamic table, right? I have to keep all subsets. Also, I have to keep the value for all subsets of the set X, right? And then also for I go through all subsets again. So I go twice through the subsets. So it's n choose I times 2 to the I here. And this is again, so it's a binomial coefficients, it's 3 to the n. Okay. Sorry. Okay, so the questions here could be, for example, you probably immediately see, so if you want to improve this type of algorithm, so here one point which is apparently is not so good. You're saying, okay, I'm doing dynamic programming and I go through all maximal sets, but in my running time estimation, I assume that I go through all subsets. But if you play a little bit, even you can do branching type of arguments, you will see immediately that if you have a graph on n vertices, that the number of maximal independent set in this graph is much less than 2 to the n. Actually, it's 3 power n over 3 at most. So this will give you immediately something better than 3 to the n. But the question, if you can do it 2 to the n, and this question, it sounds very simple, and actually people for many years, they didn't know how to do it. And then there was a breakthrough. There was a very interesting technique, which is called subset convolution. So by making using of this technique, you can solve the problem in running time 2 to the n. It's a cute algorithm, and it's not a, yes? You mean this one? Okay, so what is this? You mean this one? Or this one? Yeah, this one or this one? Okay, and choose I. Okay, so you're looking for all subsets X. How many of these sets are here? Right? And here you're looking also for a set solution 2 to the I. This is all possible subsets. This I of this set. So 2 to the I is all possible subsets of set X, which is of size I. And here you go through all subsets here, I. And this is what you keep, yeah. Yes. Yeah. So this is what you keep for your DP table, all solutions here. Right, for every set of size I, you keep the opt for every set X of size I, you keep opt of X. So in total, you keep n to the I. And to update every of these tables, you have to spend time also 2 to the I. You go through all subsets. Yeah? Yeah. Okay. Since this is a school, right? Please write down some exercises. So for people who like to branch, one problem is cluster vertex deletion. So cluster vertex, what is a cluster graph? Cluster graph is a union of cliques, right? So the question is, can I remove k vertices such that my graph will become a cluster graph? Can I remove at most k vertices such that there only cliques remains? Can you give 3 to the k algorithm for this? The other question is more interesting. So I have a minimum fill-in problem. What is a minimum fill-in problem? I have a graph. And then I ask what is a fill-in in this graph. I add edges such that after I added all these edges, there's no induced cycle of length more than 3. Right, so I'm asking if I can add at most k edges to the graph such that the result will contain no induced cycle of length more than 3. Can we solve this problem in FPT time? And actually FPT k to the k. And then, so for as a real challenge, single exponential algorithm. But here you will need a nice and cute idea to do it. It's again, everything is branching, but branching with several conditions. And then for graph coloring, that's what I was speaking about in dependent set. Just try to improve this algorithm in 3 to the n, just by any epsilon here. Right? Don't go beyond 2 to the n. That could be quite tough. But everything between 2 and 3 is doable. And actually, if you want to go just a little bit below 3, it's very doable. Just you need one more idea. You need to understand this dynamic programming and to see how you can improve it there. And the other question is also, it's a very old result of CARP. So you have a graph on n vertices, and you just try to compute the longest path. So in this graph, longest path is a graph which doesn't intersect itself. Right? So if can you compute it, this graph in 2 to the n? Yeah. Okay, so that was for, and I still have to speak about color coding. But any questions so far about branching and dynamic programming? Yes? Sorry? I don't understand. You say yes? Yes? I don't understand. So okay, so say again, or say louder. Okay, yeah. Yes? Yes?
Okay, but in your family, there can be more than UV and W, like A, B, C, D, other.
Yeah.
So you are not looking for that cases also.
Okay, yeah. So do I understand the question is, okay, so for the heating set algorithm, I just pick up some set, but my algorithm would be as far as I have a non-empty set, I just take arbitrary any set and I branch on it. Right? That's or that was not a question. Okay. Yes, and I'm just trying to find a PowerPoint. Okay, in the remaining 5 minutes, I will give you a color coding algorithm. And this is a very cute idea. And this is the algorithm of Noga Alon, Raphael Juste, and Uri Zwick. And the example of the application of color coding is a K path. I have a graph G, I have 2 vertices S and T, and I ask if there exists a simple path of length K going from S to T. Right? So simple means this path is using exactly K internal vertices. The parameter here is K. And we give an algorithm of running time to E power K. E is the base of the natural logarithm, and it's polynomial in N. Okay, but okay, anytime. So we have a problem. So what will be the trivial algorithm? That's the usual question, right? Before starting doing something clever, just try to do something silly. Okay, what will be the trivial algorithm? The trivial algorithm will be, I try all possible sets of edges in the graph, and I see for the set of edges if they form a path. If they form a path, I say good. If I never manage to find anything, I say sorry. But this running time is m, the number of edges in the graph, power k. It's not even fpt and k. Yes, and actually, okay. If we were in the normal situation, I would say I will stop here. Here's a home task for you to design any kind of FPT algorithm for k-path till the next week, right? I cannot do it, but just try to, just if you really want to appreciate this algorithm for color coding, just after my lecture, forget about color coding and try to make any FPT algorithm for k-path. It's fun. It's not simple. It's like a, okay. So, so what is this randomized algorithm is doing? I just uniformly at random, I color the vertices of my graph into k colors, right? First observation, if I have a set of k vertices, what is the probability that all vertices from this set will be colored differently? Okay, this is okay. So this is k factorial divided by k to the k, because so what is k to the k? So this is actually all possible coloring of the set S, and k factorial is the all good coloring, right? Because if I have one coloring, so if I have coloring with all different colors, with k different colors, I take any permutation of these colors, it still also will be a good coloring. So it's the probability that this set will be properly, nicely colored is k factorial times k over k. And by using natural, the standard ceiling approximations, just if you don't know this, just trust me. Here, I will not go to the calculus. So this is at least 1 over e power k. Here. And then my algorithm is the following. So I just consider a random function which assigns colors uniformly at random to vertices of the graph. And then if there exists a k path from S to T, then the probability that this path is k colorful, all vertices are of different colors, is actually significantly non-zero, right? It's quite good. And then, first of all, I just repeat my algorithm exponentially many times, like e power k times t times. And every time I'm looking, I pick a random function and I look at colorful path. And then if I find such a colorful k path, then of course my graph has a path of length k. What happened if I do not find, right? What is the probability that if my graph contains a k path, but the coloring, but I will not be able to find the colorful path? Okay, let's do this some calculation. So what will be the so this is the probability I do not find my path in one experiment, but now I repeat my experiments e power k times time t, right? So then it's I decrease the probability every time. So the probability that I fail is 1 minus this thing. And again, so here I'm using the very useful inequality that for every x at least 2, the 1 minus 1 over x power x is always between these two constants. Right? So this means that the probability that I will fail, it's 1 minus 1 over e over t. And because now this is exponential, this probability is really very close to 1. So I almost guarantee you that you will succeed in finding. Yes. So yes. So this is the algorithm. The only black box which I still we didn't open in this black box. How to find a colorful k-path. Right? Because so far it doesn't make any sense what I'm saying, right? I say, okay, I do some random coloring, and then I say, in this random coloring, it will be much easier, or I will looking for a path. But why finding a colorful path is easier than finding a normal path? Right? Colors help. First of all, this immediately gives me the algorithm of running time k power k. So what I will do, right? So if I have a colorful colored graph, and I'm looking for a colorful path. I just guess the order of the colors in this path, guess the permutation, and then the only thing what I need to find here, right? I remove actually all edges which go in the in the wrong order, which do not follow my ordering, and then here it's just it's a Dijkstra algorithm, right? I just need to find a path from S to T in this graph. Right, so if I know the colors, I can guess the ordering of the colors, which is like k factorial or k to the k, and after that I'm done. This is already FPT algorithm, but I can be a little bit smarter, and I can do dynamic programming on the number of colors to find the shortest path faster. So what I'm doing for my dynamic programming, I'm keeping the I'm keeping the value T S of V. So V is a vertex of the graph, and S is a subset of colors. And for this subset of so I say that this value is true if there exists a path from S starting in the vertex T and end in this vertex V, and this path is using all colors from S, and the length of this path is exactly S. Right? So so if I, at the end, if I compute this T of K, and here is S, I will have a solution. False otherwise. Yes. But then it's very similar to what we did for coloring, or like what we do for any kind of dynamic programming here, right? It's also very similar to Dijkstra algorithm. So basically what's happening here, so how I compute, so when I have to compute this value S of V, what I'm doing, I go through all neighbors of the vertex V, which are and then so I look for the subset of colors without the color of the vertex V, and then I look if I can use all these colors and come here, right? And if in at least in one cases I can do it, then this is true. If not, this is false. So then what's the running time of this algorithm? So what's happening here, right? So I have how many tables in my dynamic entries in my dynamic programming table I have? Well, I go through all possible subsets of colors here. So it's 2 to the k, and also through all possible vertices. It's 2 to the k times n. So the total time of dynamic programming is 2 to the k n square, right? Because I have to repeat it like n times. Okay, so now I can actually repeat the randomized algorithm. So what I'm doing, so I repeat e power k, say 100 is a random constant here. This could be 100. You can take one. I just take 100. I like for some reason 100. I don't know. Okay, so I pick a random function here, and I look for a colorful k path, right? And I know that by doing dynamic programming, I can compute colorful path in 2 to the k times n square time. So if the
coloring T of S comma V is true only when you're using exactly the colors given S to reach V from.
okay. So if the algorithm finds a k path, then definitely this is there exists a path, right? And if there exists a path, but the algorithm doesn't find it, then the probability is very small, right? And then the total running time, right? So what's happening? So I'm repeating experiment e power k times, and every time for the experiment I'm spent 2 to the k times to run the experiment. So the total running time is 2e power k some polynomial, right? And okay, so just to conclude with color coding thing. So basically, we use a very simple idea, right? So very simple idea, just use random coloring. And then the magic happens random. So when my graph is colored, it's much easier to find a colorful solution than a normal one. So here, randomization really helps a lot. Okay, I already ran 7 minutes of your coffee break, right? This is a crime. I'll stop here, and we continue after the coffee break. Okay?